0. And let's suppose we want to investigate the behavior of this function. The derivative normally is defined as the rate of change of a function, the rate of change of anything. If we talk about movement, about real motion, then we could say the rate of change of the coordinate of an object. Or we might say the rate of a chemical reaction if we look at the concentration of some substance in the reaction. So the rate of change of the concentration of this subject would define the rate of the reaction, how fast this reaction goes. Or if we are heating something, if the function depicts the temperature of something, then the gradient function or the rate of change would show how fast the temperature changes. Or if we talk about population of a city or a country, then the function would, the rate of change would mean the growth or perhaps decline of the population. So rate of change actually indicates how fast the function increases or decreases. In this case, in my example on the board, we can see that the function is increasing, and at first it increases more slowly, and then it starts increasing faster and faster and faster. And we would, of course, it's obvious why. We are looking at the graph and we are simply talking about this. But we need a mathematical way of describing this rate of change, a mathematical way of saying the rate of change is increasing, the function is growing faster and faster, for example. So we need a mathematical interpretation of this. And basically when we talk about motion, we are talking about instantaneous velocity in one specific moment. But how do we find velocity or speed? We divide the distance traveled by the time period during which this distance is traveled. So it's the difference in the coordinate divided by the interval of the time. So how do we find the instantaneous velocity, instantaneous speed? Because if I travel 100 kilometers in 1 hour, I would say, all right, my average speed was 100 kilometers per hour. It doesn't mean that at any given moment I was traveling at exactly 100 kilometers per hour. Sometimes I might be exceeding the speed, and sometimes I might be moving slowly. So it's not the instantaneous speed, it's the average speed. To find the instantaneous speed, we should do what? We should take a very short period of time, and obviously it would be a very short distance covered, and divide those. So if I decrease the time period, the distance covered in that time period also decreases, and I divide these two infinitely small quantities, and that's actually the same thing that we'll be doing with the functions. So we'll consider, for example, I want to find the rate of change of this function at the time moment, or, well, for x value, x0, we can always imagine that the x-axis depicts time, and the y-axis depicts whatever, depends on the time. And to see the rate of change of this, what we are going to do is, we will change the x value by a bit. Let's call this change delta x. It's called the increment, the x increment, or the increment of the independent variable. The x increment. So this point would have x coordinate x0 plus delta x after a bit. Now we look at the function values, at the two function values. The first function value is exactly at that given point. So it's f of x0, or we might say y0. Why not? We can call it y0, the corresponding y coordinate. So this point has coordinates x0, y0. And alright, I'll draw the horizontal line till it meets the perpendicular. And then I have this value of the function, which is, alright, f at the point x0 plus delta x. And we can call this difference, the corresponding y increment, delta y, or we can say delta f at x0, which corresponds to this value of delta x. Of course, if I take a different value, a different step for delta x, then the delta y will probably also change. So we can imagine this like I'm standing here at the point x0, I'm looking, okay, my ceiling is at this height, y0, and because I want to find the slope of the ceiling, I take a step outside, a delta x step, I look upwards and I check the height now, right? So I look at the difference of the heights, delta y. And of course I could name those points, let me see, A and B. So the point A, the point B, and I can draw a line through these 2 points. I can draw the secant for this graph. A secant is a line that intersects the graph. A secant, alright, a secant, like this, basically 2 points. And of course I can denote this by, I don't have any letter in the drawing, so I can call this D, because C will be obviously something else. Okay, so in this case I can look at this green line, and I can say that, well, obviously it has some equation, this line has some equation, and I want to remind you that the slope of this line, if this line has equation, for example, mx plus whatever b, then the slope m of this line is actually found the difference of the y values divided by the corresponding difference of the x values, if you remember. So I could write y at point B minus y at point A divided by x at point B minus x at point A. That's for any line. It doesn't have to do anything with this function, but for any line, if we have 2 points on this line, we can find the slope of this line by dividing the difference of the y values by the corresponding difference of the x values. Although in our case, in our situation, it will be obviously delta y over delta x, which is incidentally the tangent, the trigonometric tangent of this angle. The trigonometric tangent of this angle. So the slope is always the tangent of the angle that the line forms with a positive x-axis. So can I say that the slope of the line AB characterizes the rate of change of this function? On the average, perhaps, but not exactly. It depends on the length of delta x, because obviously we can say that here, we still see that here the slope is less, it's lower, and here the slope increases. The slope is not the same all the time. So I can say that the slope of the line AB more or less characterizes the average change, the average rate of change of this function, but it doesn't characterize the rate of change at any particular point. So to find the rate of change at the point A, what we can do is, let's try decreasing the value of delta x. So let's say, all right, delta x tends to 0. What's going on? What's happening? The point B is sliding, obviously, closer to the point A. So after a while, it's somewhere here, perhaps. So if delta x has decreased to this value only, and then this secant has become something like this, that would be, let's say, the point v.1. If I decrease delta x even more, the point B might slide even closer, and then the secant would be, it's difficult to sketch now. The secant would be this. So what happens when delta x is almost 0? When delta x is almost 0, when delta x becomes very, very small, what happens is that the point B is almost the same, it almost coincides with the point A. So the secant is almost the tangent line. It's almost become the tangent. So we can say that if x tends to 0, the point B approaches the point A, and actually the secant approaches the state of being the tangent line. The secant approaches the tangent actually. So this is of course all very approximate, but that's what's happening. If I decrease the value of delta x, B approaches the point A along the curve, obviously, along the graph. The secant becomes more and more like the tangent, and at the extreme situation when delta x is actually equal to 0 and B actually coincides with A, then we have obtained the tangent line. Now I have to figure out what color might work for the tangent line, probably blue. So at this point we could say now we have the tangent line, this line, AC, the tangent line, which is the extreme location, the extreme position of the secant. The extreme position of the secant. We might say in the limit language, we could say that if the slope of this is, now the thing is that B was not exactly the best way of denoting, and I'm making it, I'm changing it into B1, because it's not exactly the same as this. So kx plus b actually, some equation for the tangent. Now this is the tangent, or the tangent line. So for the tangent line, I could say that the value k, the slope k, is actually the limit when delta x approaches 0 of the ratio delta y over delta x. Or I might say the limit of f at the point x0 plus delta x minus f at point x0, that's the delta y, the difference of these two values, divided by delta x, when delta x approaches 0. And this is in fact how we define the derivative. So this number k is, first of all, it's called the derivative of this function at the point x0. So it's the derivative denoted by f prime at the point x0 of this function. It's a number. It's a number k. It's called the derivative at this point, or also called the gradient, or also called the slope of this function. So derivative, or the gradient, or the slope. Three words meaning exactly the same thing. For the function of the function f of x. In this case, we are not talking about the line anymore. We are not talking about the secant or the tangent, but we are talking about the function. In other words, the slope of the function is defined as the slope of the tangent line at that point. It's the same. The slope of this line is considered to be the slope of this function at this point. The instantaneous rate of change. The instantaneous rate of change. It's a number. Another thing to note, it is also the tangent of this angle, as we have already seen with the previous line AB. So even for the line AC, if I consider this, for example, the angle alpha, so it's the tangent of the angle alpha. And it's no coincidence that we call this the tangent line, and we see the tangent value of the angle, the trigonometric tangent. Of course, it's all connected.
And why is it called secant?
Sorry?
Why that line is called secant?
Secant because it intersects the line. Secant from the Latin roots for intersection.
actually it's like 1 over cosine.
No, secant is the secant function.
Is it?
That's something else again. Trigonometric secant is something else. Trigonometric secant is 1 over cosine, yes. The trigonometric function, the trigonometric value, that's a specific thing. But geometrically, a secant is a line that intersects the curve. For example, for a circle, the secant is any line that has 2 common points with a circle. And the tangent line would be the line that has 1 common point with a circle. So secant trigonometrically is something else than the secant geometrically. We are now talking about secant and tangent geometrically, but coincidentally or not so coincidentally, the name for the tangent line is the same as the name for the trigonometric function that defines its slope. That's an interesting thing. On the other hand, if I find the value of k, if I find the slope at every value x, not only at the point I chose right now, but at all the points of the domain of this function, then actually I will have some kind of function that for every point x from the domain of this function, every point x belonging to the domain of the function f of x, for all these points, actually I could define a function like this. The k value at this particular point. So for every point of the domain of this function, first of all, of course I have the values of the function f, but now I also have some other values. A new function, which is, in a way, we could say, it is derived from the previous function. It's obtained from the previous function. So to derive actually means to obtain from the previous function. So the derivative, the word derivative actually means something that's obtained from that other function. So we have a given function f of x, and we have the derivative or the gradient function or the slope function. Again, 3 in 1, 3 names for the same thing, which is a new function. And we say that yes, but it characterizes the slope of the original function. So it's in a way derived from the given function. If there was no given function, we couldn't find the derived function. We couldn't find the derivative. So this new function actually tells us the slope of that function at every point. At every point. So this is what we call the derivative function, or the gradient function, or the slope function, or simply the derivative of f. Simply the derivative. So that would be the meaning of the derivative. That would be why and how we obtain it. Now we need some examples, obviously. Because this is theory, this is what the derivative actually means. It means the derivative tells us how steep this blue line actually is, how steep the tangent to the graph is. If it's very steep, the derivative value is large, the high derivative, so we can say the function is actually moving upwards very fast because the angle is quite large. It's increasing fast. The rate of change is a large number. If the graph is almost horizontal, the tangent is almost horizontal, the slope is small, the slope value is small, the gradient is small, we can say that the derivative has a small value. Yes?
So from one point, we can find the slope of the line, right?
Yes, at every point we can find the slope of the line. Because if we consider this limit, it doesn't matter how far we stepped outside in the first place, because then we decrease the step until we just have a small glance upwards to see how fast the ceiling is rising above my head. All right. So using specific numbers in the function, using x0 values, we can obtain the value of the slope at every point. But if we don't use any specific value, if we try to figure out the value of this for just any generic value, any generic x, we will find the formula for this derivative function. And this is what I want to try with the function y equals x squared and then some other functions. Alright, now some specific functions. Let's repeat this. Let's try to repeat this, or at least this, for specific functions. Let's say for y equals x squared. The first example, if the function f of x is x squared. So the function f of x plus delta x, now remember composite functions, we put this into the expression of the function instead of x. So we do x0 plus delta x squared. So that would be the function value at the new point. How much exactly? Depends on x0 and depends on delta x, right? So now let's see the derivative at the point x0 of this function is lim. Why did we study limits before? For this, when delta x tends to 0, of delta f over delta x, which means delta x tends to 0. Delta f is the new value of the function minus the old value of the function. So x0 plus delta x squared minus the old value would be simply x0 squared, no brackets needed. And of course over delta x. So this is delta y or delta f, this value. So for the actual quadratic function, we can sketch the parabola. So that would mean if this is delta, if this is x0, and then this would be x0 plus delta x, we find the two values, we find the difference of the two y values. So this is x0 squared, and this is actually x0 plus delta x squared, right? This value squared. So this is what we are doing there. And now we say, okay, let delta x become very, very small. Let's see what happens to this limit. Let's see how we can use the limits to decide to see what's going on here. So lim, when delta x approaches 0, now we have to open the brackets. x0 squared plus 2 x0 delta x plus delta x squared. There's no need for brackets here because delta x is considered one symbol. It's not delta times x. It's not delta plus x. It's not two symbols. Delta x is one thing. It's this distance. So delta x doesn't really need brackets. Delta cannot be separate from x. Delta x means one specific thing. Minus x0 squared over delta x. Now we see these two cancel out. And if we divide this, the remaining part, if we divide the remaining part by delta x, we have 2x0 times delta x divided by delta x, it becomes simply 2x0 plus delta x squared divided by delta x becomes simply delta x. And now, if delta x tends to 0, this is the thing that changes in this limit, then the value of this limit will be equal to x0. Because we are considering the fixed point x0 of this function. And if I change the value of x0, if I take any other point from the real numbers, then I can say that for every point I can find the gradient by this formula. So I can say that x squared derivative actually equals to x. And this is the derivative of the function y equals x squared. The derivative of this function, so I can write it this way, f prime of x is 2x, which means the same thing. So I can write it like this. I can write f of x is this, then f prime of x, the derivative is this. I can write it like this, x squared in brackets prime, derivative is this. There's another notation, dy over dx, which is also used. So we can actually also use the notation dy by dx. It's the same, well, I will explain this notation when we approach integration. The differential of the function divided by the differential of the independent variable x. We will look more at this notation and what it actually means when we approach integration. The differential of a function, what kind of thing is this? Is this the same as delta y? Not exactly. Not exactly. But that's a notation that you will encounter sometimes. You will see it. Or maybe not sometimes, but often. Alright, so now if I consider this function, I have found a formula for the derivative of the quadratic function. Now I will try to draw a more accurate sketch. Okay, something like this. Hopefully it looks more like a parabola. Alright, so I can say that if x is 1, then the derivative, if x is 1, then the derivative equals 2. So at this point I can sketch the tangent line. At this moment it's just visually what it looks like. And I would say that obviously the slope, the gradient of this line should be equal to 2. Because it has to be 2 times 1 at this point. So yes, we can say it is approximately 2. You can consider one step right, 2 up. So the slope of this line is actually 2. So for the sake of comparison. Obviously, if I choose x value 1/2, then the slope would be 1, which means at the point where x is 1/2, the tangent line should be at 45 degrees, because tangent of 45 degrees equals 1. What happens if x is 0? What happens if x is 0? The slope is 0 by calculation. By geometry, what happens? The tangent line is horizontal. So for the horizontal lines, we do know that for a horizontal line, the slope equals 0. So if x is 0, the formula tells us that the derivative is equal to 0 at that point. And geometrically, we'll also see this. The tangent line is horizontal and its slope indeed does equal 0. Can the slope be negative? Yes, why not? If x is negative for this function, for example, if x is -1, then the slope should be -2. And yes, it is. The slope is -2. You see, 1 right, 2 down, 1 right, 2 down. So the slope for this would be -2. We can have negative slope, which means the function is decreasing. If the rate of change is negative, velocity is negative, it means it's decreasing. The function is decreasing. If the slope is 0, it means at this moment, at this point, the function has stopped decreasing. It's at standstill, if you like. And then after this point, it starts increasing. The slope becomes positive. So I'm showing you all this simply to make note or point out the meaning, the geometric meaning of the slope, the geometric meaning of the derivative. So we can see that the function x squared, the derivative of this function is 2x. Now let's try to find some other derivatives. Let's simply try to find some other derivatives for some other functions. What kind of examples do I have there? Linear function. All right, let's do the linear function ax plus b. So if f of x, the next function is ax plus b, a straight line. A straight line, we can say it doesn't change its rate of change. The slope doesn't change. For a straight line, the slope is the same all the time. So the derivative should be constant, actually. Let's try. So f, all right, let's write the limit. F derivative is lim as delta x tends to 0. F at the point x0 plus delta x will be a times x0 plus delta x plus b minus the function value at the old point is simply ax0 plus b divided by delta x. So for any point x0, we have now ax0 minus ax0, these two cancel out. Out. Now b minus b cancel out. And now we have a times delta x divided by delta x. Obviously, delta x cancel out. So yes, we have a constant a. The derivative of a linear function is equal to its slope, of course. Of course, the gradient is the slope. So now we see that analytically, doing it by formulas, it also fits. It also matches the situation geometrically. Of course, we understand that a straight line has a constant slope. It doesn't start growing faster or slower. The slope doesn't change. It's always the same for all x values. And it's equal to the first coefficient, of course. So from this, we can also see that the slope of a constant function of a horizontal line obviously has to be 0. According to all this, if we have a equal to 0, a horizontal line, y equals to b, we can see that b minus b is 0. The slope will be actual 0. So we can see that the constant derived is 0. An interesting thing. Now let's have a look at two more functions. And then we'll stop the definition by first principle, so derivatives by first principles, derivatives by definition. That will be all for now. So let's take function 1 over x. Let's take the function 1 over x, and let's find the derivative of this function. So it's lim when delta x tends to 0. I'm stopping. I won't do x0 anymore. I'm simply putting for any value x, we can find the formula. So I won't write x0 anymore. I will simply write x to make it faster and simpler. So I should have 1 over x plus delta x at the new point, minus the value at the old point, and all of that divided by delta x. Now I have to simplify this. This is not pleasant, this is complicated. Let's try to simplify this expression. Lim, never lose the limit. So how do we simplify this? Find the common denominator. The common denominator for these two quotients would be x plus delta x times x. So it would be multiplied by x minus multiplied by x plus delta x. And all this is this part. I have written now, this part is written there. And to divide it all by delta x, of course, I write delta x in the denominator, down there. Now let's see what's going to happen. X minus x, these will cancel out. So I have minus delta x remaining in the limit limit, x tends to 0, minus delta x remains in the numerator. In the denominator, I have x plus delta x times delta x. Now I can cancel out delta x. So this would be minus 1 now, minus delta x divided by delta x. And now, if delta x tends to 0, we can ignore it. We have minus 1 divided by x squared. If delta x tends to 0, we can ignore it here. Yeah, okay. I'm glad that you agree, because it's important that you do understand what's going on. So we see that the derivative of the function 1 over x, of the reciprocal function, is minus 1 over x squared. So that's another formula. We can write that 1 over x derivative is minus 1 over x squared. Another formula. Number 5, let's take the square root. So the derivative of this is all the limits. Delta x tends to 0. Square root of x plus delta x minus square root of simply x. And, okay, I won't use brackets. Divided, of course, by delta x. Well, familiar limits. 0 over 0. Uncertainty. We have been doing this. Nothing is new under the sun. Nothing is new. So I can multiply, as we used to do, by the conjugate expression, square root x plus delta x plus square root of x, divided by the same, x plus square root x plus delta x plus square root of x. So now I get x plus delta x minus x plus delta x without the root now, minus, again, the square of this is x without the root now. And here we have delta x times square root of x plus delta x plus square root of just delta x. Now, okay, cancel out. If we divide everything by delta x, we have limit delta x tends to 0, 1 over square root x plus delta x square plus square root of x. And now, if the final step, if delta x tends to 0, we can ignore it. We have 2 identical square roots. So it's 1 over 2 square roots of x. So that's the derivative of the square root function. Square root function derived is 1 over 2 square roots of x. Meaning that at any point of the domain, which is all the non-negative numbers, 0 or positive, at any point of the domain, I can find the slope of this graph, of this function, by applying this formula for all values of x. All right.
I'm sorry.
It would be, yes.
So for example, for the log solution, is that so necessary to so for example,
the definition, I understand. You want, is it necessary to do the definition all the time? No. Of course, to establish the laws so that we don't have to do the limits all the time, to establish the laws, we would need to prove them. We don't have time, so you will have to believe me and trust me that I'm giving you the correct laws, but they can be proved in a similar manner. So there are not so many laws for today. We can have 1, 2, 3, maybe 4 laws for today. There are more. Today we start with the simplest ones. So normally what I do in class at school, I would also offer the function x cubed to be derived by definition by using limits, and then I would ask the students to guess what the derivative of, for example, x to the fourth would be, or x to the fifth. Yes, usually they do guess well. So in this case, I'm simply going to tell you the derivative of x cubed is 3x squared, the derivative of x to the fourth is 4x cubed, and now you probably, those who don't know yet, can deduce the law of powers of x. Hopefully, or not.
And multiplied by x in the power n minus.
Yes, that's true. So the first law is, if I have the power x to the power, I will write a derived is a times x to the power a minus 1. In other words, the exponent, when deriving, the exponent becomes the coefficient, and the actual exponent of this power function gets decreased by 1. I'm not writing n because when we write n, we generally presume natural numbers, positive integers, but I write a because we can prove, we just won't, we can prove that a could be any real number. It could be negative because in this case n is minus 1. So it should be minus 1 times x to the power minus 2, which is exactly it. So yes, it works for negative integers. It follows that simply x derived is 1, or as we saw, the derivative of a linear function is simply the coefficient of this linear function. A constant means x to the power 0 times constant. Obviously, the 0 becomes a factor, so it's 0. And so we need the derivative of a constant term is actually 0. Now we also need basic laws. So this is simply the first formula for derivatives, but we also have some basic laws. The first law would be, if I multiply a function by some constant, by a coefficient k, so k is some real number, then the derivative of this function is the same constant times the derivative of this function. In other words, if I have to derive something like 4 to the power x squared, the 4 remains there, and I only derive x squared, so it will be 8x. Please note, this is again a common mistake. If the constant is multiplied by the function, it remains there. If the constant stands alone as a term, as an addend, then it gets lost, because it has no x to hold it down, let's put it that way. So this is why the derivative of this function is simply a, because b is a single constant, a standalone constant. The derivative of a simple single constant is 0. Which brings us to the final law. If I have the sum, or perhaps the difference of two functions, so for example, if I have a polynomial, and I want to derive a polynomial, so I can do it each term separately. I can do f function separately, plus or minus g function derived separately. So these are the basic laws for today. No more laws, no more theory today, now only exercises. Okay, so page 3, there are 4 exercises, and then page 4, more exercises. We have 40 minutes. Well, obviously not so much time for everything. So in exercise 1.1, if you look at exercise 1.1, there you have very simple functions, simple polynomials. So this is good practice for those who have either completely forgotten this material from school or who have never seen this before. So that would be exercise 1.1, very good for just recalling these things. Now 2 and 3 is a little bit more complicated for other people. Yes?
Where can I take an answers?
Answers, I will send them to you. I have them. I do have them. All right, I can. Perhaps I can get them on my screen, and you can take a picture if you like. I'll see. This is not connected to the internet. I haven't acquired the mobile internet yet for this.
Why don't you use the Wi-Fi?
They haven't given me the password.
It's your login for Office.
Yeah.
It's my login for orders.
Yes,
If I have that, I'm not sure if I do.
you should have.
Because
You
I have been just a guest teacher, so nobody has bothered to give me. I don't
But you have a
have.
section mathematics in Office,
Yes.
but no login name whatsoever.
So I will try to settle this with the office. They should give me a login name and a password.
Or some
Obviously.
job.
They should. So okay, let's see. Yes. Come on. Okay. Derivative answers. All right. Have it there. Okay. Okay. So if you want to come and take a picture of the answers, they are here. There
Turn
might
the
be
laptop
some
around.
slight mistakes. I have been checking and correcting them, but okay. This is all right. It's decided. No. It's decided to
What? No, I can zoom in.
save the energy because I've been using it today. Okay.
Smile for the camera.
That's the first one and the second page. Yes. Oh, okay.
Honestly, what are you going here, right?
First page is the important one. You probably
just see my
won't get
face.
it at the moment. I'm using, I'll email this to everybody. No problem.
So now it's nothing.
No, it is.
Okay,
I
what
changed
for?
it to SD card.
Iced card.
Yes.
Iced tea.
I changed to a SD card.
Aha, SD card. Okay, I said iced tea card. I was like, shit, what's that? Can you go home and like just do it home?
The paper versions, unfortunately, have been some of the first ones. Okay. Okay, the game. Okay. master. It takes practice. It's not a conscious thing. It takes practice to acquire the correct movements instinctively. So it takes time. It's very new. So I haven't. Listen, x is because you cannot divide by 0. So 0 does not belong. 0 is not in the domain. That's the only thing. But for number 3, you have to open the brackets in order to derive. Don't try to apply quotient rule or any other rule. Simply open the brackets and it will be much easier to find the derivative.
For example, can I do 2 different buttons in number 8?
No. You have to open the brackets because there's a special rule for products. There's a special rule for products of functions, and that's something that we will cover probably next time. Yes. You should write this is obviously x square root of x, or x to the power 1/2. This would be x to the power 2, minus 1/2. You have to be very careful with these. So if you don't remember product rule or quotient rule well, then I would really advise you in number 3, in exercise 1.3, to open the brackets and differentiate that way. In exercise 2, you have to transform this function into a power of x. If you transform the function into a power of x, then you can derive it easily, or the sum of powers of x. Then they can be derived easily. Stop.
Regarding next week or in 2 weeks, will be the one and fast forward.
I know it's I have to do it soon because otherwise there will be new papers and it's the snowball effect. I have to do it soon. I'm halfway through with those. I'll try to manage them on Saturday because on Sunday I'm asleep. So minus 3 times x to the power minus 2. Because this is actually, it is x to the power minus 3. And if you derive it, you have to take this. It becomes the coefficient times x minus 3 minus 1. It's minus 4. So it becomes minus 3 over x to the 4.
Like the same, like restaurant, you don't go every day.
Let me remind you to there is no just email what's required to email and
Which is it? It's 7. Okay, so